Welcome to my channel. Today we're going to learn how a three-phase induction motor works. I'll explain it step by step in a simple way. Let's get started. When we apply a DC voltage to a wire, current starts flowing. This current creates a magnetic field that swirls around the wire in circular loops like invisible rings. Which way do these magnetic circles go? Use the right-hand rule. Point your thumb in the direction of the current and your fingers will curl in the direction of the magnetic field. This beautiful phenomenon is known as the curl rule. Extend your right hand, point your thumb along the direction of the current and watch as your fingers naturally curl, tracing the invisible path of the magnetic field around the wire. Permanent magnets create a steady magnetic flux between their poles. When a DC current-carrying conductor loop is placed within this magnetic field, the current generates its own magnetic flux around the loop. In some regions, the conductor's magnetic flux opposes the flux from the magnets, leading to a repulsion effect. In other regions, the two fluxes align and reinforce each other. Through vector addition of these magnetic fields, a net force is produced, causing the loop to experience a torque and rotate. The sides of the loop experience forces in opposite directions. One side of the loop is pushed upward, while the other side is pushed downward. This creates a turning effect, or torque, causing the loop to start rotating. According to Fleming's right-hand rule, where the forefinger represents the magnetic field, the middle finger the current, and the thumb the force, to keep the rotation continuous, a commutator is used, which reverses the direction of the current after every half turn. This way, the forces always act in the same rotational direction, allowing the loop to spin steadily as long as the DC current is applied. When we apply AC current to a wire, something very interesting happens, and it's almost instantaneous. As the current flows through the wire, it produces a fluctuating magnetic field around it. As the AC wave changes direction, the magnetic field around the wire responds instantly. It doesn't stay still, it flips its direction too, in perfect synchronization with the oscillating current. This constant back and forth creates a dynamic, pulsating magnetic field that mirrors the rise and fall of the AC wave, almost like a heartbeat of energy flowing through the wire. Now let's see how this copper loop concept is used inside an induction motor. Instead of a simple loop, many copper conductors are placed in the stator slots, all around the inner surface of the stator. The stator of this motor has 18 slots evenly distributed around its inner circumference. These slots hold 9 coils, carefully arranged to create a balanced three-phase winding. Each phase is connected to 3 coils, spaced 120 electrical degrees apart. Let's visualize how the magnetic field is created in a three-phase induction motor, step by step, phase by phase. We begin with phase A. As current flows through the winding of phase A, it generates a magnetic field, shown here as a pulsating flux. This field expands and contracts, pointing along its winding axis. Next, phase B is energized, 120 degrees out of phase with phase A. Its magnetic flux appears, also pulsating, but shifted in space and time. Now, we introduce phase C, the third phase, again 120 degrees apart. Its flux adds to the system, completing the three-phase flux pattern. The stator is powered by 3 alternating currents. Each current is offset by 1/3 of a cycle, or 120 electrical degrees, creating a time difference between them. The stator windings are also placed 120 degrees apart in space. To create a balanced and continuous rotation in space, the stator windings must also be placed carefully. Here's the trick. Instead of spacing them 120 degrees apart physically, we adjust one of the windings, usually the one that's 240 degrees out of phase, and connect it in reverse. This flips its magnetic field direction. Now all 3 magnetic fluxes are evenly spaced 60 degrees apart in space. The result? A perfectly balanced, smooth and rotating magnetic field that keeps the motor running efficiently. Each magnetic flux in a three-phase induction motor is 60 degrees offset from the others. Through the vector addition of the magnetic fluxes from all 3 phases, They combine to form a rotating magnetic field in the stator winding. The rotating magnetic flux spins around the rotor, creating the effect of a moving magnetic field. This spinning flux acts just like an invisible permanent magnet, with a north pole and a south pole that rotate around the rotor. Even though there's no physical magnet, it looks as if a magnetic field with rotating poles is circling the rotor, constantly cutting through the rotor bars and setting the motor in motion. From the rotor's point of view, it appears as though it is spinning clockwise while the rotating magnetic flux remains constant in space. This relative motion between the rotor conductors and the stationary magnetic flux causes the flux to cut across the rotor bars. According to Faraday's right-hand rule, this cutting action induces an electric current in the rotor bars. Now, stationary point of view, the rotor is at rest while the magnetic flux is rotating. As this rotating magnetic field sweeps past the rotor bars, it cuts through them and changes over time. According to Faraday's law, this changing magnetic field induces electric current in the rotor conductors. These induced currents then create their own magnetic field, which interacts with the stator's rotating field and produces torque. Now, according to Lenz's law, this induced magnetic field opposes the motion that created it. In this case, the rotating magnetic field. As a result, the rotor experiences a force that pulls it in the same direction as the rotating field. This interaction creates torque, and the rotor begins to spin, gradually accelerating toward the speed of the magnetic field. As the rotor begins to spin, it tries to catch up with the rotating magnetic field created by the stator. But in reality, it never quite reaches the same speed. This difference in speed is called slip. Slip is essential for the motor to work. If the rotor were to spin at exactly the same speed as the magnetic field, there would be no relative motion between them. That means no magnetic field would cut through the rotor bars. And without that, no current would be induced. Without induced current, there's no torque, and the motor would stop. So the rotor always stays slightly slower than the rotating magnetic field. This small difference keeps the induction process going, allowing the motor to continue producing torque and running efficiently. Thank you for watching this video. If you found it helpful, please like, share, and subscribe to stay updated with our latest uploads. See you next time.